17 equations written on a single page that explain nearly everything humans have ever understood about the universe. The shape of space, the motion of planets, the behavior of light, the structure of atoms, the flow of information, the price of risk. Each equation fits on a single line. Each one took centuries to discover, and each one, once discovered, changed what was possible, not just in mathematics but in the physical world, in the technology, in the daily life of every person alive. Tonight, we are going to walk through those equations, one at a time, slowly. Not the notation, you don't need to read the symbols to understand the stories. Each equation is a story, a person, a problem, and a revelation that changed everything that came after it. And the equations are not isolated. They build on each other. Each one rests on the shoulders of the ones before it, and the ones that follow could not exist without it. You don't need to understand the notation. You don't need to know what the symbols mean. The stories behind the equations are more powerful than the symbols themselves, because the stories tell you not just what the equations say, but what they cost, the years of effort, the flashes of insight, the personal tragedies, and the transformations that followed each discovery. The page of 17 equations is not a list, it is a chain, and the chain stretches from ancient Greece to the trading floors of Wall Street. We'll follow the chain from ancient Greece, where a theorem about triangles destroyed the worldview of the people who discovered it, through 17th century England, where a single equation made it possible to predict the future, through 19th century Scotland, where 4 equations revealed that light is electricity, through 20th century Vienna, where an equation replaced certainty with probability, and onto the trading floors of late 20th century New York, where an equation that was supposed to eliminate risk nearly destroyed the global economy. All of it, slowly, for sleep. The oldest equation on the page is 2,500 years old, and you already know it. In a right triangle, the square of the longest side equals the sum of the squares of the other two sides. If the two shorter sides are 3 and 4, the longest side is 5, because 9 plus 16 is 25, and the square root of 25 is 5. The theorem is named after Pythagoras of Samos, a Greek philosopher and mathematician who lived in the 6th century before the Common Era. Whether Pythagoras himself proved the theorem is uncertain. The Pythagoreans, his followers, attributed all discoveries to the master, and disentangling Pythagoras' own work from that of his school is probably impossible. What is not uncertain is that the relationship was known long before Pythagoras. Babylonian clay tablets from roughly 1800 years before the Common Era contain lists of Pythagorean triples, sets of 3 numbers satisfying the relationship, suggesting that Babylonian mathematicians understood the theorem 1,000 years before Pythagoras was born. Indian mathematicians also knew the relationship. The Sulba Sutras, texts on geometric constructions dating to roughly 800 years before the Common Era, contain explicit statements of the theorem and methods for constructing right angles using Pythagorean triples. The theorem's independent discovery by multiple civilizations suggests that it is not a cultural artifact, but a mathematical inevitability. Any civilization that studies right triangles carefully enough will discover the relationship between the squares of the sides. The theorem is not imposed on geometry by human imagination. It is found in geometry by human observation. It was always there, in every right triangle that has ever existed, waiting to be noticed. But the Pythagorean theorem is not just a fact about triangles. It is the equation that defines distance. If you want to know the straight line distance between 2 points in a plane, you draw a right triangle with the 2 points at opposite corners and apply the theorem. The horizontal distance is one side. The vertical distance is the other. The hypotenuse is the distance you want. The theorem has been proved more times than any other result in mathematics. Over 400 distinct proofs have been published by amateurs and professionals alike, using methods from algebra, geometry, trigonometry, and even physics. One proof, discovered by a member of the United States Congress and published in 1876, uses a trapezoid divided into 3 right triangles. The congressman was James Garfield, who would become the 20th President of the United States 5 years later. His proof is elegant. Arrange 2 copies of the right triangle and a third triangle into a trapezoid. Compute the area 2 ways, set the results equal, and the Pythagorean theorem falls out. A future president proved a 2,300-year-old theorem using nothing but the area formula for a trapezoid. One proof is attributed to a 12-year-old James Garfield, who later became the 20th President of the United States. Another uses nothing but scissors and rearrangement. You cut the squares on the two shorter sides into pieces and reassemble them into the square on the hypotenuse, like a jigsaw puzzle. The sheer number of proofs suggests that the theorem sits at a crossroads in mathematics, reachable from almost any direction. Every distance calculation you've ever seen, in a GPS, in a video game, in an architectural plan, is the Pythagorean theorem in disguise. The theorem extends beyond flat surfaces. In 3 dimensions, the distance between 2 points is the square root of the sum of the squares of the differences in all 3 coordinates. The Pythagorean theorem applied to 3 dimensions instead of 2. In Einstein's general relativity, the concept of distance is generalized further using what is called a metric tensor. But the underlying idea that distance is computed from the squares of the coordinate differences traces directly back to Pythagoras' equation. The Pythagorean theorem also destroyed the Pythagorean worldview. The Pythagoreans believed that all numbers are rational, expressible as ratios of whole numbers. But the hypotenuse of a right triangle with both short sides equal to 1 is the square root of 2, and the square root of 2 is irrational. The proof of this irrationality, which we've encountered in earlier stories, shattered the Pythagorean belief that whole number ratios govern everything. The equation that bears their name contains a number their philosophy couldn't accommodate. The square root of 2 is irrational. Its decimal expansion goes on forever without repeating. 1.41421356237. The digits continue without pattern, without end, without ever settling into a repeating cycle. The Pythagoreans had believed that every number could be expressed as a fraction. The hypotenuse of their own triangle proved them wrong. The equation that defined their geometry destroyed their arithmetic. This was the first of many times in the history of mathematics that an equation would reveal a truth its discoverers didn't want to hear. Equations don't care about your worldview. They state what is, regardless of what you wish were true. And the Pythagorean theorem stated with perfect clarity that irrational numbers exist, numbers that no fraction can name, numbers that no ratio can capture, numbers that are as real as 1 and 2 and 3, but fundamentally different in kind. Let those numbers settle. 3, 4, 5, the simplest Pythagorean triple. Known to the Babylonians 4,000 years ago. Known to the Egyptians who used knotted ropes in ratios of 3, 4, and 5 to create right angles for building the pyramids. Known to the Chinese, who recorded Pythagorean triples in the Jobi Suanjing roughly 1,000 years before the Common Era. The theorem doesn't belong to any single civilization. It belongs to mathematics, which is to say it belongs to everyone and to no one. The Pythagorean theorem is the foundation. Every equation that follows tonight rests on it, directly or indirectly, because every equation involves quantities that are measured, and measurement involves distance, and distance is the Pythagorean theorem. In higher dimensions, the theorem extends naturally. In 3 dimensions, the distance between 2 points is the square root of the sum of the squares of the differences in all 3 coordinates. In 4 dimensions, you add a 4th squared term. In any number of dimensions, the pattern continues, and in Einstein's spacetime, the distance between 2 events, the spacetime interval, is calculated using a modified version of the Pythagorean theorem, where the time component enters with a negative sign rather than a positive one. The most fundamental quantity in all of relativity is a generalized Pythagorean distance. The theorem is 2,500 years old, and it runs deeper through mathematics and physics than any other single result. Every equation that follows tonight uses distance, and distance is the Pythagorean theorem. There is another ancient equation that deserves mention before we leave the world of pure mathematics for the world of physics, the quadratic formula, which gives the solutions to any equation of the form x squared plus bx plus c equals 0, was known in various forms to the Babylonians 4,000 years ago, to Indian mathematicians by the 6th century, and to Islamic mathematicians by the 9th century. Al-Khwarizmi, whose name gives us the word algorithm, described the method of completing the square, the technique underlying the quadratic formula, in his foundational algebra text of the early 9th century. The quadratic formula matters not because it is beautiful, it isn't particularly, but because it represents the idea that equations can be solved. Given a problem expressed as an equation, you can find the answer using a systematic procedure. This idea, which seems obvious now, was revolutionary when it first appeared. Before algebra, problems were solved by trial and error, by geometric construction, or by clever tricks specific to each problem. The quadratic formula showed that an entire class of problems could be solved by a single method, applied mechanically, producing the answer every time. This idea, that general methods exist for solving general classes of problems, is the central idea of algebra, and it is the intellectual foundation for every equation on tonight's list. Newton's F equals ma is solved using techniques from algebra and calculus. Maxwell's equations are solved using techniques from vector algebra. Schrödinger's equation is solved using techniques from linear algebra. The equations are from physics, but the methods for solving them are from algebra, and algebra began with the quadratic formula. The story of equation solving didn't end with quadratics. The cubic formula was discovered in the 16th century by Italian mathematicians Del Ferro, Tartaglia, and Cardano. The quartic formula for fourth-degree equations followed shortly after, but the quintic, equations of degree 5, resisted every attempt. In 1824, the Norwegian mathematician Niels Henrik Abel proved that no general formula exists for the quintic, and in 1832, the French mathematician Évariste de Galois, at the age of 20, developed a complete theory explaining exactly which equations can be solved by formulas and which cannot. Galois died in a duel the next year, at 20. He spent the night before the duel writing down his mathematical ideas in a frantic series of letters and manuscripts, scribbling, "I have no time," in the margins. The work he produced that night laid the foundations of group theory, one of the most important branches of modern algebra. The theory of equations, which began with the quadratic formula 4,000 years ago, reached its deepest expression in the work of a 20-year-old who died before he could publish it. The duel was fought on May 30th, 1832. Galois was shot in the abdomen and left on the ground by his opponent. He was found by a passing farmer and taken to a hospital, where he died the next day. He was 20 years old. The night before the duel, knowing he might not survive, Galois wrote letters to friends summarizing his mathematical ideas. The letters are frantic, brilliant, and heartbreaking. In the margins, he wrote, "I have no time, and there is something to complete in this demonstration." The complete theory that he sketched in those desperate hours would take other mathematicians decades to understand and develop, and it forms the foundation of modern abstract algebra. Galois' story is the most tragic in the history of mathematics. A genius who understood, at 20, truths about the structure of equations that the greatest mathematicians alive couldn't see. Killed in a duel over a matter that historians have never fully explained. Possibly a romantic dispute. Possibly a political provocation. The mathematics survived. The mathematician did not. The equations of mathematics are not always about physics. Some of the most important equations describe growth, biological, economic, social. The logistic equation, which describes how populations grow when resources are limited, says that the rate of growth is proportional to both the current population and the fraction of the carrying capacity that remains unused. When the population is small relative to the carrying capacity, growth is approximately exponential, fast, accelerating, unchecked. As the population approaches the carrying capacity, growth slows and eventually stops. The resulting curve, the S-curve or sigmoid, appears in biology, epidemiology, marketing, technology adoption, and dozens of other fields. The logistic equation is also famous for exhibiting chaos. When the equation is iterated in discrete time steps rather than solved continuously, it produces behavior that is deterministic but unpredictable. The output depends sensitively on the initial conditions, jumping chaotically between values in a pattern that appears random but is entirely determined by the equation. This discovery, made by the biologist Robert May in the 1970s, was one of the founding results of chaos theory, and showed that simple equations can produce arbitrarily complex behavior. If the Pythagorean theorem is the equation that defines distance, the next equation on our page defines the relationship between shapes and space itself. It was discovered by Leonhard Euler in 1750, and it says something so simple about solid objects that it seems like it should have been obvious. except nobody noticed it for the entirety of recorded mathematical history before Euler. Take any solid shape with flat faces, a cube, a tetrahedron, a dodecahedron, any polyhedron. Count the vertices, the points where edges meet. Count the edges, count the faces. The number of vertices minus the number of edges plus the number of faces always equals 2. The formula is easy to verify. Take a cube, 8 vertices, 12 edges, 6 faces. 8 minus 12 plus 6 equals 2. Take a pyramid with a square base. 5 vertices, 8 edges, 5 faces. 5 minus 8 plus 5 equals 2. Take a dodecahedron, the 12-sided regular solid made of pentagons. 20 vertices, 30 edges, 12 faces. 20 minus 30 plus 12 equals 2. Try any convex polyhedron you like. The answer is always 2. The number 2 in this context is called the Euler characteristic. For a convex polyhedron, any solid with flat faces, straight edges and no holes, the Euler characteristic is always 2. But if you poke a hole through the solid, creating a donut shape, the Euler characteristic drops to 0. 2 holes, -2. The Euler characteristic counts something fundamental about the shape, its topology, its essential connectivity, and this counting is the beginning of one of the deepest branches of modern mathematics. A cube has 8 vertices, 12 edges, and 6 faces. 8 minus 12 plus 6 equals 2. A tetrahedron has 4 vertices, 6 edges, and 4 faces. 4 minus 6 plus 4 equals 2. Every convex polyhedron satisfies this formula. No exceptions. Euler's polyhedron formula, V minus E plus F equals 2, seems like a curiosity, a pretty pattern with no practical importance. But it turned out to be the first theorem in a branch of mathematics called topology, the study of properties that are preserved when shapes are stretched, bent, and deformed without tearing or gluing. The number 2 in Euler's formula is a topological invariant. It doesn't change when you deform the polyhedron, as long as you don't poke holes in it. A donut-shaped polyhedron, which has a hole through it, gives a different number, V minus E plus F equals 0. The number tells you the shape's topology, how many holes it has. Topology turned out to be one of the most important branches of mathematics, with applications in physics, computer science, data analysis, and the study of the shape of the universe itself. The Euler characteristic, the number V minus E plus F, turned out to be one of the most important invariants in all of mathematics. It classifies surfaces. A sphere has Euler characteristic 2. A torus has 0. A double torus has -2. Each additional hole decreases the Euler characteristic by 2. The number tells you at a glance the fundamental topology of the shape. How many holes it has, how it's connected, how it relates to other shapes. In the 20th century, topology became one of the central branches of mathematics with connections to physics, computer science, and data analysis. The classification of manifolds, the higher dimensional analogues of surfaces, is one of the great achievements of modern mathematics, and it began with Euler's simple observation about polyhedra, the 4-color theorem, the result that any map can be colored with at most 4 colors such that no 2 adjacent regions share a color, is a topological result that connects to Euler's formula through the theory of planar graphs. The theorem was proved in 1976 with the assistance of a computer, making it the first major mathematical theorem whose proof relied on computational verification. The proof was controversial precisely because it required a computer. Many mathematicians felt that a proof you can't check by hand isn't really a proof. The debate about computer-assisted proofs continues, but the theorem itself is now accepted, and it started with Euler counting corners, edges, and faces, and noticing that the sum was always 2. Between Euler's polyhedron formula and the equations that follow, there is a shift. The first 2 equations, the Pythagorean theorem and Euler's formula, describe static objects, triangles, polyhedra, shapes that sit still and let you examine them. The equations that follow describe things that move, things that change, things that flow and oscillate and radiate. The shift from static to dynamic is the shift from geometry to physics, and it is the most important transition in the history of mathematics. If you are drifting off, that is fine. The equations don't need you to be awake. They've been true for centuries, and they'll be true whether you hear them tonight or not. But if you're still with me, the next equation is the one that made the modern world possible, and it was written down by a man who was also sitting in a farmhouse during a plague. Force equals mass times acceleration. F equals ma. 3 letters that describe every motion you have ever seen, from a falling leaf to a launching rocket to the orbit of the moon around the Earth. Isaac Newton was 23 years old when he first formulated the relationship between force, mass, and acceleration. Working in isolation at his family farmhouse in Woolsthorpe during the plague years of 1665 and 66, he didn't publish the result for another 20 years, partly because he was afraid of criticism, partly because the mathematical framework needed to express the result properly didn't exist yet, and Newton had to invent it. The framework was calculus, which Newton invented largely for this purpose. The Principia was written in roughly 18 months, a period during which Newton worked with an intensity that alarmed his friends. His servant reported that he rarely ate, sometimes forgot to dress, and would stand frozen in his room for hours, lost in thought. The book was written not by a calm scholar at a comfortable desk, but by a man in the grip of an intellectual compulsion so powerful that it displaced basic human needs. The Principia is divided into 3 books. The first develops the mathematical framework, the laws of motion and their consequences. The second applies the framework to the motion of objects through resisting media, air, water. The third applies it to the solar system, deriving the orbits of planets, moons, and comets from the law of universal gravitation. The third book, called The System of the World, is one of the most ambitious intellectual achievements in human history, a mathematical description of the entire observable universe derived from 3 laws of motion and 1 law of gravity. Newton's second law of motion, published in the Principia Mathematica in 1687, is the equation that turned physics from a qualitative description of the world into a quantitative science capable of prediction and engineering. The equation looks simple: 3 quantities multiplied together. But the simplicity is deceptive, because each quantity hides enormous depth. Force is not a single number. It is a vector with both magnitude and direction. So is acceleration. The equation actually says that the force vector equals the mass times the acceleration vector, and when multiple forces act on an object simultaneously, you add them as vectors, and the resulting total force determines the acceleration. The equation also codifies the concept of inertia, the tendency of an object to resist changes in its motion. Mass is the measure of inertia. Heavy object is hard to accelerate, not because something is holding it back, but because mass itself is resistance to acceleration. This is the content of Newton's first law. An object in motion stays in motion unless acted upon by a force, and the second law quantifies it. The bigger the mass, the smaller the acceleration for a given force. The concept of mass seems simple until you ask what it is. Why do objects have mass? Why do some have more than others? Newton couldn't answer these questions. It took until 2012, when the Higgs boson was discovered at the Large Hadron Collider, for physicists to confirm the mechanism by which fundamental particles acquire mass. The Higgs mechanism, proposed independently by Peter Higgs and several others in the 1960s. The mass that appears in Newton's equation, the m in F equals ma, is at the deepest level a consequence of interactions with the Higgs field that permeates all of space. The full machinery of vector calculus is implicit in those 3 letters. But the equation's real power becomes visible when you combine it with a specific force law. Newton's law of universal gravitation says that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Plug this force into F equals ma, and you get a differential equation whose solutions are the orbits of planets, moons, comets, and satellites. The inverse square law explains why planets close to the Sun orbit faster than planets far away. It explains why the Moon stays in orbit rather than flying off into space or crashing into the Earth. It explains the precise elliptical shape of every orbit in the solar system. All of these facts, which Kepler discovered empirically through years of painstaking observation, fall out of Newton's equation in a few pages of calculus. The equation also predicts phenomena that Newton couldn't observe. It predicts that two massive objects orbiting each other will gradually lose energy through gravitational radiation, a prediction confirmed by observations of binary pulsars in the 1970s and by the direct detection of gravitational waves in 2015. The equation is also a differential equation. It relates the acceleration of an object, which is the second derivative of its position with respect to time, to the forces acting on it. Solving F equals ma for a specific situation means solving a differential equation, and the solution gives you the object's position as a function of time. The entire trajectory, past, present, and future, is encoded in the equation and the initial conditions. Before Newton, people knew that heavy objects fall. They knew that thrown objects follow curved paths. They knew that planets move in ellipses. But they didn't know why. They couldn't predict where a cannonball would land. They couldn't calculate the orbit of a comet. They couldn't design a bridge or a machine or a building with mathematical precision. They observed. They built by trial and error, and they guessed. Newton's equation changed everything because it connects cause to effect with mathematical precision. The force on an object, the push or pull it experiences, determines its acceleration, which is the rate at which its velocity changes. If you know the force, you can calculate the acceleration. If you know the acceleration, you can calculate the velocity at any future moment. If you know the velocity, you can calculate the position. Force gives you acceleration. Acceleration gives you velocity. Velocity gives you position. The chain runs forward through time, linking cause to consequence through a single equation. Every rocket launched into space is a solution to Newton's equation. The engineers calculate the forces, thrust, gravity, air resistance, and the equation tells them the trajectory. Every bridge designed by an engineer is a solution to Newton's equation, applied to static structures, where the acceleration is zero and the forces must balance. Every aircraft in flight is a continuous solution to Newton's equation. The thrust from the engines, the drag from the air resistance, the lift from the wings, and the weight from gravity all contribute forces that Newton's equation combines into a trajectory. The pilots don't solve the equation in their heads. The flight computers do it continuously, thousands of times per second, adjusting control surfaces to maintain the desired trajectory. Every satellite in orbit follows a path dictated by Newton's equation. The trajectory is calculated before launch and corrected periodically using small thruster burns. The GPS satellites that tell your phone where you are orbit at an altitude of roughly 20,000 kilometers. Completing 2 orbits per day, each orbit a solution to Newton's equation for an object under the Earth's gravitational pull. The precision of your location on a map depends on the precision with which Newton's equation predicts the satellite's positions. Every car crash analyzed by a forensic investigator is reconstructed using Newton's equation, working backward from the damage to determine the forces and speeds involved. Newton himself used his equation to derive Kepler's laws of planetary motion from the single assumption that gravity decreases as the square of the distance. Kepler had discovered empirically that planets move in ellipses. Newton showed mathematically that they must move in ellipses because the inverse square gravitational force, combined with F equals ma, produces elliptical orbits as the only possible solution. Kepler's first law says planets move in ellipses with the sun at one focus. Newton showed that this follows from the inverse square law of gravity combined with F equals mb. Kepler's second law says a planet sweeps out equal areas in equal times. Newton showed that this follows from the conservation of angular momentum. Kepler's third law says the square of the orbital period is proportional to the cube of the semi-major axis. Newton showed that this follows from the mathematical properties of elliptical orbits under inverse square gravity. 3 empirical laws painstakingly extracted from astronomical observations over 20 years by Kepler, derived in a few pages of mathematics by Newton from a single equation and a single assumption. The power of the derivation is difficult to overstate. It transformed astronomy from a descriptive science, recording what the planets do, into an explanatory science, understanding why the planets do what they do. And the explanation is simple. They do it because F equals ma, and the force is gravity, and gravity falls off as the square of the distance. Observation became explanation. Description became prediction, and the equation that made it possible fits on a line. But solving it, Applying it to specific situations and extracting the trajectory of an object from the forces acting on it requires all the mathematical machinery of calculus. The equation is a differential equation. It relates the acceleration, which is the second derivative of position with respect to time, to the forces acting on the object. Solving it means integrating the equation, finding the function whose second derivative satisfies the force law. For simple cases, like a ball thrown in the air under uniform gravity, the integration is straightforward. For complex cases, like three bodies orbiting each other under mutual gravitational attraction, the integration has no closed-form solution and must be done numerically. The three-body problem. The problem of predicting the motion of three objects under mutual gravity has no general solution in closed form. This was proved by Henri Poincaré in the 1890s, and the result launched the field of chaos theory. Even Newton's simple equation, applied to just three objects, produces behavior so complex that no finite formula can describe it. The simplicity of the equation and the complexity of its solutions are two sides of one coin. Newton's equation also made engineering possible in a way it hadn't been before. Before Newton, bridges were built by intuition and tradition. Techniques passed from master to apprentice, refined by trial and error over centuries. After Newton, bridges could be designed by calculation. You specify the loads, you calculate the forces, you determine the stresses, you choose materials strong enough to handle them. The bridge works not because the builder has decades of experience, but because the equation is right. An identical transformation happened in every field of engineering. Machines, vehicles, buildings, ships, all of them, after Newton, could be designed on paper before being built in steel. The gap between imagination and construction was bridged by F equals ma and the differential equations it generates. Newton's equation also explained the tides. The gravitational pull of the moon on the Earth's oceans combined with the rotation of the Earth produces the twice-daily rise and fall of sea level. The tidal force is the difference in gravitational pull between the near side of the Earth and the far side, a calculation that requires Newton's equation applied to extended bodies rather than point particles. Tidal prediction, which is crucial for navigation, fishing, and coastal engineering, is a direct application of F equals ma and the law of universal gravitation. The equation didn't just describe the world, it made the world designable. There is a subtlety in Newton's equation that is easy to miss. The m, mass, appears on both sides of a deeper equation as gravitational mass, which determines how strongly an object is attracted by gravity, and as inertial mass, which determines how much an object resists acceleration. Newton noticed that these two masses are always equal, but couldn't explain why. Einstein explained it 3 centuries later. Gravitational mass and inertial mass are equal because gravity isn't a force at all. It's the curvature of space-time. Objects in freefall aren't being pulled by a force, they're following the straightest possible path through curved space. The equality of gravitational and inertial mass, which Newton took as an unexplained coincidence, became the foundation of general relativity. The next equation on our page connects 5 numbers from different centuries and different branches of mathematics in a relationship so unexpected and so elegant that it has been called the most beautiful equation ever written. E to the power of I times pi plus 1 equals 0. 5 constants, e the base of the natural logarithm, approximately 2.718. I, the square root of -1, a number that was called imaginary for centuries because nobody believed it was real. Pi, the ratio of a circle's circumference to its diameter. 1, the multiplicative identity. And 0, the additive identity, the number that took millennia to invent and that was banned in parts of medieval Europe. 3 operations, exponentiation, multiplication, and addition. 1 equation, 1 result, 0. Euler published the identity in the 18th century, during the most productive mathematical career in history. He was blind for the last 17 years of his life, and his output increased rather than decreased. He dictated papers from memory, computing in his head what other mathematicians needed pages of paper for. The identity that bears his name is his most famous result, but it is one of roughly 800 papers and books he published across every branch of mathematics that existed in his time. This is Euler's identity, and it follows from a more general formula that Euler derived in the 18th century. E to the I theta equals cosine theta plus I sine theta. set theta equal to pi, and cosine pi is -1. Sine pi is 0, so e to the I pi equals -1. Add 1, 0. The identity connects arithmetic and geometry, algebra and analysis, the discrete and the continuous. E comes from calculus and the study of growth. I comes from algebra and the solution of polynomial equations. Pi comes from geometry and the measurement of circles. 1 and 0 come from the foundations of arithmetic. These 5 numbers were discovered by different people, in different centuries for different reasons, and they are linked, exactly and inevitably, by a single equation. The first time I truly felt the weight of Euler's identity, I was writing out the Taylor series for e to the x, for sine x, and for cosine x side by side. The series are e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Sine x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Cosine x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. When you substitute ix for x in the exponential series and separate the real and imaginary parts, you get the cosine series plus I times the sine series. The identity doesn't drop from the sky. It rises from the structure of the series, and the structure is there whether anyone notices it or not. Euler noticed. Let that settle. 5 constants, 3 operations, 1 equation. The equation doesn't explain why these 5 numbers are connected. It just states the connection, the explanation, if there is one, if explanation even applies deeper than any single proof, in the structure of mathematics itself. Euler's identity is sometimes dismissed as a mathematical curiosity, beautiful but useless, elegant but impractical. This is wrong. The formula from which the identity derives, e to the I theta equals cosine theta plus I sine theta, is one of the most practically important results in all of mathematics. It converts between exponential functions and trigonometric functions, which means it converts between growth and oscillation. In electrical engineering, the formula converts oscillating voltages and currents into rotating complex numbers, enormously simplifying the analysis of alternating current circuits. An alternating current which oscillates sinusoidally can be represented as the real part of a rotating complex exponential. This representation turns differential equations into algebraic equations, reducing problems that would take pages of trigonometric manipulation to a few lines of complex arithmetic. Every electrical engineer uses Euler's formula daily, usually without thinking about the fact that the mathematics connecting exponentials to trigonometry was discovered 3 centuries ago by a blind Swiss mathematician. In electrical engineering, it simplifies the analysis of alternating currents. In signal processing, it's the foundation of the Fourier transform. In quantum mechanics, it's the natural language for describing wave functions. The beauty and the utility are inseparable. If you are drifting, let the identity drift with you. It connects 5 numbers from 5 different centuries through 3 operations in 1 equation. The connection was there before Euler found it. It will be there after everyone who knows about it is gone. Mathematical truth is the most durable thing in existence, and Euler's identity is among its most perfect expressions. We have covered distance, shape, motion, and the unity of constants. The next equation unified something far more dramatic: electricity, magnetism, and light. The story of Maxwell's equations begins not with Maxwell but with Michael Faraday, a self-educated English experimentalist who discovered electromagnetic induction in 1831. Faraday showed that a changing magnetic field produces an electric current, the principle behind every electric generator and every transformer. He also introduced the concept of a field, an invisible entity that fills space and transmits forces, which replaced the older idea of forces acting at a distance through empty space. Faraday was the son of a blacksmith, self-educated, with almost no formal schooling. He began his scientific career as a laboratory assistant to Sir Humphry Davy at the Royal Institution in London, and rose through talent and persistence to become one of the greatest experimental scientists in history. He discovered electromagnetic induction, which makes electric generators and transformers possible. He discovered the laws of electrolysis. He discovered diamagnetism. He introduced the concepts of field and lines of force that would become the foundation of Maxwell's mathematical theory. The gap between Faraday's experimental discoveries and Maxwell's mathematical formulation of them is one of the most dramatic gaps in the history of science. Faraday could see the fields. He visualized them as lines of force spreading through space, curving around magnets, linking electrical circuits. He could describe what the fields do, but he couldn't write equations for them because he didn't have the mathematical training. Maxwell had the mathematical training. He took Faraday's visual intuition and expressed it in the precise language of partial differential equations. Faraday was a brilliant experimentalist, but had little mathematical training. He described his results in words and diagrams rather than equations. Maxwell took Faraday's physical insights and translated them into the language of mathematics, producing a set of equations that captured everything Faraday had discovered and more. In the 1860s, the Scottish physicist James Clerk Maxwell published a set of 4 equations that described the behavior of electric and magnetic fields. The equations say electric charges produce electric fields. Magnetic field lines never end. There are no magnetic monopoles. A changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. The last 2 equations are the revolutionary ones. A changing magnetic field creates electricity. A changing electric field creates magnetism. Electricity and magnetism are not separate forces. They are aspects of a single force, electromagnetism, and they feed on each other. A changing electric field creates a changing magnetic field, which creates a changing electric field, which creates a changing magnetic field, and on, the fields sustaining each other as they propagate through space. Maxwell calculated the speed at which these self-sustaining electromagnetic waves would travel. He took the known constants of electricity and magnetism, plugged them into his equations, and got a number, approximately 300 million meters per second. That number was already known. It was the speed of light, measured independently by astronomical and laboratory experiments. The match was too precise to be a coincidence. Maxwell wrote in one of the great understatements in the history of science, "We can scarcely avoid the inference that light consists in the transverse undulations of that medium which is the cause of electric and magnetic phenomena." Translation: light is an electromagnetic wave. Light is electricity and magnetism, oscillating together, traveling through space at the speed that Maxwell's equations predict. The unification of electricity, magnetism, and light was one of the great intellectual achievements of the 19th century. Before Maxwell, these were 3 separate phenomena studied by 3 separate communities of scientists. Electricians studied electricity. Magneticians studied magnetism. Opticians studied light. After Maxwell, they were one phenomenon, electromagnetism, and the distinctions between them were merely differences of frequency. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all electromagnetic waves, differing only in wavelength. Maxwell's equations describe them all with equal precision. The concept of unification, showing that apparently different phenomena are manifestations of a single underlying reality, became one of the guiding principles of physics after Maxwell. Einstein unified space and time into spacetime. The electroweak theory unified electromagnetism with the weak nuclear force. The Standard Model of particle physics unifies 3 of the 4 known forces. The quest for a grand unified theory that encompasses all 4 forces is the direct descendant of Maxwell's unification of electricity, magnetism, and light. Every time physicists unify 2 apparently different phenomena under a single mathematical framework, they are following Maxwell's template. The template is: write down the equations, find the symmetries, and let the mathematics reveal the connections that observation alone can't see. The Standard Model of particle physics, completed in the 1970s, unifies 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, under a single mathematical framework based on gauge symmetry. The framework is beautiful, predictive, and confirmed by every experiment ever performed at particle accelerators. But it doesn't include gravity. Unifying gravity with the other 3 forces remains the central unsolved problem in theoretical physics, and the solution, if it comes, will be an equation that extends the chain one more link. Before Maxwell, light was a mystery. After Max C, light was a solution to a set of differential equations. The equations predicted that electromagnetic waves should exist at all frequencies, not just the frequency of visible light. Heinrich Hertz confirmed this prediction experimentally in 1888, detecting radio waves for the first time. The electromagnetic spectrum, which Maxwell's equations predict, extends from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than an atom. Visible light occupies a tiny sliver of this spectrum, roughly from 400 to 700 nanometers. Everything above and below visible light was predicted by Maxwell's equations before it was detected. Radio waves by Hertz in 1888, X-rays by Röntgen in 1895, and gamma rays by Villard in 1900. Every radio, every television, every cell phone, every Wi-Fi signal, every microwave oven, every X-ray machine is a consequence of Maxwell's equations. The technology of the modern world is Maxwell's equations made physical. Maxwell was a quiet, modest man whose importance to physics is rivaled only by Newton and Einstein. He was born in Edinburgh in 1831, showed mathematical brilliance as a child, and studied at Cambridge, where he was second in the mathematical tripos examination. He held professorships at Aberdeen and King's College London before returning to Cambridge to establish the Cavendish Laboratory, which would become one of the most important physics laboratories in the world. His electromagnetic theory was not immediately accepted. The concept of a field, an invisible entity filling space, was unfamiliar to many physicists who preferred the older picture of forces acting at a distance. It took Hertz's experimental confirmation of electromagnetic waves in 1888, 9 years after Maxwell's death, to convince the skeptics. Maxwell died of cancer in 1879 at the age of 48. Einstein kept a photograph of Maxwell on his study wall, alongside photographs of Newton and Faraday. When asked if he had stood on Newton's shoulders, Einstein reportedly replied, "No, I stand on Maxwell's shoulders." The cascade of technology that followed Maxwell's equations is staggering in its scope. Hertz detected radio waves in 1888. Marconi transmitted them across the Atlantic in 1901. By the 1920s, radio broadcasting was a global industry. By the 1940s, radar, radio detection and ranging, was saving lives in World War II, detecting enemy aircraft at distances that gave defenders crucial minutes of advance warning. The radar systems that defended Britain in 1940 were solutions to Maxwell's equations applied to the specific problem of detecting metal objects by bouncing radio waves off them and measuring the time delay of the echo. The physics is Maxwell's. The engineering is radar. The consequence was survival. Without radar, without Maxwell's equations, the Battle of Britain might have been lost, and the course of the war might have been different, detecting enemy aircraft at distances that changed the outcome of the Battle of Britain. By the 1950s, television was in every living room. By the 1970s, communications satellites were relaying signals across the globe. By the 2000s, cell phones were in every pocket, streaming data through electromagnetic waves at frequencies Maxwell's equations describe with perfect precision. Every one of these technologies is a solution to Maxwell's equations. The equations tell you how to generate electromagnetic waves, how to transmit them, how to receive them, how to focus them, how to modulate them to carry information. The equations don't care what information you carry. Voice, video, text, data. They describe the medium. The message is up to you. There is another equation hiding inside Maxwell's equations that deserves its own moment. The wave equation, the equation that describes how a disturbance propagates through a medium, was known before Maxwell. It describes how sound travels through air, how ripples travel across water, how vibrations travel along a string. The equation says that the acceleration of the disturbance at any point is proportional to the curvature of the disturbance at that point. The more sharply curved the wave, the faster it accelerates. This one relationship, acceleration proportional to curvature, produces all wave phenomena: interference, diffraction, resonance, standing waves, harmonics. When Maxwell combined his electromagnetic equations, the wave equation dropped out naturally. The electric and magnetic fields satisfy a wave equation, and the speed of the wave is determined by the electromagnetic constants. That speed is the speed of light. Maxwell didn't postulate electromagnetic waves, he derived them. The waves were hiding inside the equations, waiting to be noticed. The wave equation connects an enormous range of phenomena that seem unrelated on the surface. Sound waves in a concert hall, seismic waves from an earthquake, light waves from a star, gravitational waves from colliding black holes, all described by variants of one equation. Musical instruments are wave equation machines. A vibrating string on a guitar produces sound at frequencies determined by the wave equation applied to a string with fixed endpoints. The fundamental frequency and the harmonics, the overtones that give each instrument its distinctive timbre, are solutions to the wave equation. The mathematics of music is the mathematics of waves, and both are the mathematics of one equation relating acceleration to curvature. Gravitational waves predicted by Einstein in 1916 and detected by LIGO in 2015 are waves in the fabric of space-time itself. They are produced by the most violent events in the universe: colliding black holes, merging neutron stars, exploding supernovae, and they carry information about these events across billions of light years. The wave equation that describes gravitational waves is derived from Einstein's field equations, not from Newton's mechanics, but the mathematical structure is recognizably the same: acceleration proportional to curvature, disturbance propagating at a finite speed. The universality of the wave equation is one of the most striking examples of the unity of physics. Phenomena that look completely different are governed by mathematics that is structurally identical. If you are still with me, the next equation introduces a concept so profound and so counterintuitive that it took decades for physicists to accept its implications. The equation is Boltzmann's entropy formula, and it governs the direction of time. S equals k times the logarithm of W. S is the entropy of a system, a measure of its disorder, its randomness, its number of possible arrangements. K is Boltzmann's constant, a fixed number that connects the microscopic world of atoms to the macroscopic world of temperature and pressure. And W is the number of microscopic arrangements, microstates, that correspond to the same macroscopic state. Consider a deck of cards. A shuffled deck has high entropy because there are an enormous number of possible arrangements, roughly 8 times 10 to the 67th, and almost all of them look random. A sorted deck has low entropy because there is essentially one arrangement that counts as sorted. Entropy measures how many ways the microscopic details can be arranged without changing the macroscopic appearance. The second law of thermodynamics is sometimes called the most fundamental law in all of physics. Arthur Eddington, the astronomer who confirmed Einstein's general relativity, wrote that if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. The second law says that entropy, Boltzmann's S, never decreases in an isolated system. It can stay constant. It can increase, but it never goes down. The universe moves in one direction toward disorder, toward randomness, toward the most probable state. The second law of thermodynamics says that entropy never decreases in an isolated system. Things go from ordered to disordered, from unlikely to likely, from special to generic. This is not a tendency or a preference. It is a statistical inevitability, as certain as the law of large numbers, and for essentially that reason, there are overwhelmingly more disordered arrangements than ordered ones. So any random change is overwhelmingly likely to increase disorder. Consider a room with all the air molecules on one side. This is an extremely low entropy state. The molecules are concentrated, ordered, arranged in an improbable configuration. If you wait, the molecules will spread throughout the room, moving toward the high entropy state of uniform distribution. This happens not because a law commands it, but because there are astronomically more ways for the molecules to be spread out than concentrated. Every random collision, every molecular interaction pushes the system toward the more probable state. The second law is a consequence of counting. That principle explains why hot coffee cools, why ice melts, why perfume diffuses, why tidy rooms get messy, and why you can't unscramble an egg. Each of these processes is a transition from a low entropy state to a high entropy state, from an improbable arrangement to a more probable one. Ice melts. Hot coffee cools. Perfume diffuses through a room. None of these processes reverse spontaneously, because the reverse would require a transition from a high entropy state to a low entropy state, which is overwhelmingly improbable. Boltzmann's equation explains why. The number of disordered arrangements vastly exceeds the number of ordered ones. A system that starts in an ordered state will, through random interactions, almost certainly end up in a disordered state, simply because there are so many more disordered states to land in. The second law isn't a law in the way F equals ma is a law. It's a statistical fact, a consequence of probability applied to astronomical numbers of particles. This is where entropy meets the arrow of time. The laws of physics, Newton's laws, Maxwell's equations, Schrödinger's equation, are all time reversible. They work equally well forward and backward. If you film a ball bouncing and play the film in reverse, the reversed motion obeys Newton's laws perfectly. But if you film an egg breaking and play it in reverse, nobody believes the reversed film is real. Eggs break, they don't unbreak. That asymmetry, the difference between forward and backward in time, comes from entropy. The past had lower entropy. The future has higher entropy. And the reason the past had lower entropy is one of the deepest unsolved problems in physics. The universe started in an extraordinarily low entropy state, the hot, dense, uniform plasma of the Big Bang. From that improbable beginning, entropy has been increasing ever since, driving every irreversible process in the universe. But why did the universe start in a low entropy state? The laws of physics don't require it. A high entropy beginning would have been overwhelmingly more probable. The low entropy initial condition is a fact about our universe that the laws of physics don't explain. It is the one fact that gives time its direction, and nobody knows why it's true. Some physicists, notably Roger Penrose, have argued that the low entropy beginning requires a special explanation, a new law of physics or a constraint on the initial conditions that the current theory doesn't provide. Others, notably Sean Carroll, have proposed that our universe is a local low-entropy region in a larger multiverse, where entropy fluctuations occasionally produce conditions suitable for the emergence of structure, life, and observers. The debate is ongoing, and the answer may require a theory of quantum gravity that doesn't yet exist. The second law, extrapolated to its logical conclusion, predicts the heat death of the universe, a state of maximum entropy in which all energy is uniformly distributed. No temperature differences exist, no work can be done, and nothing happens. Every star has burned out, every black hole has evaporated. The universe is a uniform, featureless expanse of extremely low energy radiation at a temperature barely above absolute zero. This state is the maximum entropy endpoint of the universe, and the second law says the universe is heading toward it. The heat death is not expected for an unimaginably long time, roughly 10 to the 100th years, a number so large that writing it out would fill pages. But the trajectory is set. The arrow of time, powered by the increase of entropy, points toward the heat death, and nothing in known physics can reverse it. Boltzmann's equation, carved on his tombstone, is one of the most poignant memorials in the history of science. The equation represents everything he fought for: the reality of atoms, the statistical nature of thermodynamics, the connection between microscopic chaos and macroscopic order. His opponents denied all of this. They said atoms were useful fictions, not real objects. They said thermodynamics was an exact science, not a statistical one. They said Boltzmann's approach was philosophically confused and mathematically unnecessary. Boltzmann fought back with lectures, papers, and public debates. He was a passionate, emotional man, charismatic in the lecture hall, devastating in debate, and deeply wounded by professional criticism. His defense of the atomic hypothesis was both a scientific argument and a personal crusade, and the constant opposition took a terrible psychological toll. Boltzmann's entropy formula didn't just explain the direction of time, it also set fundamental limits on the efficiency of engines. The Carnot efficiency, the maximum fraction of heat that any engine can convert to useful work, is a direct consequence of the second law of thermodynamics, which Boltzmann's formula makes precise. Every car engine, every power plant, every refrigerator operates within limits set by entropy, and those limits cannot be exceeded by any technology, no matter how advanced. The laws of thermodynamics are the ultimate engineering constraints, and Boltzmann's equation is their mathematical expression. Ludwig Boltzmann fought for decades to convince the physics community that atoms are real and that thermodynamics is statistical mechanics. The mechanics of enormous numbers of particles whose individual motions are unpredictable, but whose collective behavior follows precise statistical laws. Many prominent physicists of his era, including Ernst Mach and Wilhelm Ostwald, rejected the atomic hypothesis and considered Boltzmann's statistical approach to be a philosophical error rather than a scientific advance. Boltzmann suffered from severe depression throughout his life. In 1906, while on vacation with his family near Trieste, he hanged himself. He was 62. His tombstone bears his entropy formula, S equals co-log W. The equation outlived the man and outlived every objection his opponents raised. Within a year of Boltzmann's death, Jean Perrin's experiments on Brownian motion provided definitive evidence for the existence of atoms, and the atomic hypothesis that Boltzmann had defended was accepted by the entire physics community. Mach, Ostwald, and the other anti-atomists quietly revised their positions. The man who had been driven to despair by professional rejection was vindicated by experiment within months of his death. Atoms are real. Thermodynamics is statistics, and the arrow of time is a consequence of counting, of the overwhelming preponderance of disordered states over ordered ones. If you are still awake, we have passed the halfway point. Behind us, the geometry of triangles, the topology of polyhedra, the mechanics of motion, the unity of constants, the nature of light, and the direction of time. Ahead, the equivalence of mass and energy, the probability of the quantum world, the mathematics of information, the price of risk, and the flow of fluids. Each equation ahead builds on the ones behind it. The chain continues. The most famous equation in the world is also the shortest, E equals mc squared. Energy equals mass times the speed of light squared. Albert Einstein was 26 years old, working as a patent clerk in Bern, Switzerland, when he published this equation. 1905 was Einstein's miracle year. He published 4 papers, each of which would have been the achievement of a career. The first explained the photoelectric effect using the concept of light quanta, essentially inventing quantum mechanics. The second proved the existence of atoms by explaining Brownian motion. The third introduced the special theory of relativity, overturning the Newtonian concepts of absolute space and absolute time. And the fourth, a short addendum to the relativity paper, derived E equals mc squared. No scientist before or since has had a year like 1905. Einstein's situation in 1905 was extraordinary. He had completed a doctorate but couldn't find an academic position. He had applied to multiple universities and been rejected. He worked at the Swiss Patent Office in Bern, examining patent applications for electromagnetic devices. The job was steady, but intellectually unstimulating, and Einstein did his physics in his spare time, scribbling equations during breaks and after hours. The contrast between Einstein's professional obscurity and the magnitude of his achievements is one of the great stories in the history of science. The patent clerk who couldn't get a university teaching position produced, in a few months, work that transformed physics permanently. He would later develop the general theory of relativity, which replaced Newton's theory of gravity with a geometric theory of curved space-time. But the 4 papers of 1905, produced in obscurity, without colleagues, without a laboratory, without institutional support, represent the most concentrated burst of scientific genius in recorded history. Albert Einstein published this equation in 1905 in a short paper that was almost an afterthought to his special theory of relativity. The equation says that mass and energy are interchangeable, matter is frozen energy, energy is liberated matter, and the conversion factor, the speed of light squared, is enormous, roughly 90 quadrillion in metric units. A small amount of mass corresponds to a staggering amount of energy. This equation explains why the sun shines. In the sun's core, hydrogen nuclei fuse together to form helium. The helium nucleus has slightly less mass than the hydrogen nuclei that formed it. The missing mass, roughly 0.7%, has been converted to energy according to Einstein's equation. That tiny percentage, multiplied by c squared, produces enough energy to power the sun for billions of years. The equation also explains nuclear weapons. The fission of a uranium nucleus releases energy because the fragments have slightly less total mass than the original nucleus. The mass difference, multiplied by c squared, produces the devastating energy of an atomic bomb. The bomb that destroyed Hiroshima converted roughly 1 gram of matter into energy. 1 gram, the weight of a paperclip, releasing the energy equivalent of 15,000 tons of dynamite. The Nagasaki bomb, 3 days later, used plutonium instead of uranium and was even more powerful. Together, the two bombs killed roughly 200,000 people and forced Japan's surrender, ending World War II. The physics of nuclear weapons is E equals mc squared applied to nuclear binding energies. The binding energy of a nucleus, the energy needed to pull it apart into its constituent protons and neutrons, depends on the type of nucleus. When a heavy nucleus like uranium splits into lighter fragments, the total binding energy increases and the excess energy is released. The amount of energy released per atom is tiny, but a kilogram of uranium contains roughly 2.5 times 10 to the 24th atoms, and the cumulative energy release is enormous. That equation governs nuclear power, which produces roughly 10% of the world's electricity. Nuclear reactors use that fission process as nuclear weapons, but controlled. The chain reaction is moderated so that energy is released slowly and steadily rather than all at once. The equation also underlies positron emission tomography, PET scans, which are used in medical imaging to detect cancer, study brain function, and diagnose heart disease. A PET scan works by injecting a radioactive tracer into the patient. The tracer emits positrons, antimatter particles, which annihilate with electrons in the patient's body, producing pairs of gamma rays. The gamma rays are detected and their positions are reconstructed to form an image. The annihilation of matter and antimatter, with the conversion of mass to energy according to E equals mc squared, is the physical process that makes PET scanning possible. The energy that lights cities and powers submarines comes from one equation that leveled Hiroshima, releasing the energy equivalent of 15,000 tons of dynamite. The equation also explains why particle accelerators work. When you accelerate a proton to nearly the speed of light, its kinetic energy becomes comparable to its rest mass energy, mc squared. At the Large Hadron Collider, protons are accelerated to such extreme energies that the collisions can create new particles, particles that didn't exist before the collision, whose mass is created from the kinetic energy of the colliding protons. The Higgs boson, discovered in 2012, was created this way. Its mass, roughly 125 times the mass of a proton, was conjured from pure energy, exactly as Einstein's predicts. The equation connects the very large to the very small. It explains why stars shine, a process involving astronomical scales. It explains why radioactive atoms decay, a process involving subatomic scales. And it connects both through a single relationship between mass and energy that holds at every scale, in every context, without exception. No equation in physics has a broader range of validity. Einstein himself was deeply troubled by the military applications of his equation. He signed a letter to President Roosevelt in 1939 warning that Germany might develop an atomic bomb, a letter that contributed to the creation of the Manhattan Project. After the war, he spent much of his remaining years advocating for nuclear disarmament. The equation that bears his name is neither good nor evil. It is a fact about the universe. The uses to which it is put are human choices, not mathematical consequences. Einstein wasn't finished after E equals mc squared. His most profound equation, the one he considered his greatest achievement, came 10 years later. The Einstein field equations of general relativity, published in 1915. These equations describe how the geometry of spacetime is shaped by the presence of mass and energy. The field equations are written as g mu nu equals 8 pi g over c to the 4th times t mu nu. The left side, g mu, describes the curvature of spacetime. The right side, t mu nu, describes the distribution of matter and energy. The equation says, matter tells spacetime how to curve, and spacetime tells matter how to move. This reciprocal relationship, matter shaping geometry, geometry guiding matter, is the essence of general relativity and the deepest understanding of gravity that physics has achieved. In Newton's theory, gravity is a force that acts between objects. In Einstein's theory, gravity is not a force at all. It is the curvature of space-time itself. Massive objects curve the space-time around them, and other objects follow the curves. They move along the straightest possible paths through curved space, which appear, from a distance, to be the curved trajectories of gravitational attraction. The field equations are notoriously difficult to solve. Each solution describes a different space-time geometry, a different configuration of mass, energy, and curvature. The Schwarzschild solution, found within a month of Einstein's publication, describes the space-time around a non-rotating spherical mass and predicts the existence of black holes, regions where the curvature becomes so extreme that nothing, not even light, can escape. The Friedmann solutions, found in the 1920s, describe an expanding or contracting universe and provided the theoretical foundation for the Big Bang theory. Einstein's field equations predicted gravitational waves, ripples in the fabric of space-time, produced by the acceleration of massive objects, propagating outward at the speed of light. These waves were detected directly for the first time in September 2015 by the LIGO Observatory, 100 years after Einstein predicted them. The detection confirmed the last major untested prediction of general relativity and opened a new field of astronomy, gravitational wave astronomy, in which the universe is observed not through light but through the trembling of space-time itself. The Einstein field equations are among the most beautiful and the most difficult equations in all of physics. They are beautiful because they express a profound insight that gravity is geometry in a compact mathematical form. They are difficult because they are non-linear. The curvature of space-time depends on the distribution of matter, but the distribution of matter depends on the curvature of space-time, which depends on the distribution of matter in an endless loop. Solving the equations requires finding a self-consistent solution to this loop, and in most cases, exact solutions are impossible. Numerical methods, solving the equations approximately on computers, are required for most practical applications, from modeling the merger of two black holes to simulating the large-scale structure of the universe. Even your GPS system requires corrections from general relativity. The clocks on GPS satellites, orbiting at high altitude in weaker gravity, tick slightly faster than clocks on the ground. Without the correction predicted by Einstein's equations, roughly 38 microseconds per day, GPS positions would drift by roughly 10 kilometers per day, making the system useless within hours. Let that settle for a moment. We have moved from the shape of triangles to the interconvertibility of matter and energy. The equations are getting deeper, the consequences more dramatic, and the physics more strange. What comes next is the strangest of all. In 1926, the Austrian physicist Erwin Schrödinger published an equation that describes how quantum systems evolve over time. The Schrödinger equation is to quantum mechanics what F equals ma is to classical mechanics, the master equation from which everything else can be derived. But there is a crucial difference. Newton's equation tells you the position and velocity of an object at every moment in time. Schrödinger's equation tells you the wave function of a system, a mathematical object that encodes the probabilities of all possible measurement outcomes. The wave function doesn't tell you where a particle is. It tells you where a particle might be, and how likely each possibility is. The wave function is a complex-valued function. It assigns a complex number to every point in space and every moment in time. The complex number has both a magnitude and a phase, like a wave with both a height and a position in its cycle. The probability of finding the particle at a given location is the square of the magnitude of the wave function at that location. The phase, which determines how different wave functions interfere with each other, is responsible for the distinctly quantum phenomena of interference and superposition. The Schrödinger equation tells you how the wave function evolves over time. It is a partial differential equation. It relates the time derivative of the wave function to its spatial derivatives, and solving it for specific situations gives you the wave function at every moment, which gives you the probability distribution at every moment. For a hydrogen atom, the solutions to Schrödinger's equation are the atomic orbitals, the shapes you see in chemistry textbooks, the s orbitals and p orbitals and d orbitals, each one a different standing wave pattern of the electron around the nucleus. Niels Bohr had proposed in 1913 that electrons orbit the nucleus only at specific, discrete energy levels, not at any energy, as classical physics would predict, but only at certain allowed values. Bohr's model was revolutionary, but ad hoc. It stated the allowed energies without explaining why those particular values were allowed. Schrödinger's equation provided the explanation. The allowed energies are the eigenvalues of the equation, the values for which the equation has well-behaved solutions. The discrete energy levels that Bohr had postulated emerge naturally as the eigenvalues of Schrödinger's equation. The entire structure of the periodic table follows from the solutions to this one equation. This probabilistic character is not a limitation of our knowledge, it is a feature of reality. Before a measurement is made, the particle doesn't have a definite position. It exists in a superposition of all possible positions, with the probability of each one given by the wave function. The measurement forces the particle to choose, the wave function collapses to a single value, and the outcome is genuinely random. Not random because we don't know enough, random because the universe itself doesn't determine the outcome until the measurement is made. Schrödinger's equation governs the behavior of atoms, molecules, and subatomic particles. It explains why atoms have discrete energy levels, why chemical bonds form, why materials conduct electricity or don't, why lasers work, and why semiconductors are possible. Every electronic device you own, every computer, every phone, every television, was designed using principles derived from Schrödinger's equation. Without Schrödinger's equation, there would be no transistors. Without transistors, there would be no computers. Without computers, there would be no internet, no smartphones, no digital technology of any kind. The entire digital revolution rests on the solutions to a wave equation derived by an Austrian physicist during a 2-week Alpine vacation in 1925. The practical applications extend beyond electronics. Magnetic resonance imaging, which produces detailed images of the interior of the human body, works by manipulating the quantum states of hydrogen nuclei and detecting their responses. The quantum states are described by Schrödinger's equation. Laser technology, which underpins everything from barcode scanners to fiber optic communication to eye surgery, works by stimulating quantum transitions in atoms. The transitions are governed by Schrödinger's equation. The semiconductor chips that run the modern world are engineered at the quantum level, using the wave functions and energy levels that Schrödinger's equation predicts. The transistor, the fundamental building block of all digital electronics, works because of quantum tunneling, a phenomenon in which particles pass through barriers that classical physics says are impassable. The probability of tunneling is calculated from Schrödinger's equation. The design of every transistor in every chip in every device you own depends on this calculation. The laser, used in barcode scanners, DVD players, fiber optic communication, eye surgery, industrial cutting, and 1,000 other applications, works by stimulated emission, a quantum mechanical process described by Schrödinger's equation. Einstein predicted stimulated emission in 1917. The first working laser was built in 1960. The equation predicted the phenomenon 4 decades before the technology existed to exploit it. Schrödinger derived his equation during a 2-week vacation in the Swiss Alps in December 1925, reportedly in the company of a mistress whose identity has never been established. The equation he produced is a wave equation. It describes how a wave evolves over time, but the wave it describes is not a physical wave in space. It is a probability wave, a mathematical object whose squared magnitude gives the probability of finding a particle at a given location. The transition from physical waves to probability waves was one of the hardest conceptual leaps in the history of physics. Schrödinger wanted his waves to be physical. He wanted the electron to literally be a wave, spread out through space, oscillating. Max Born proposed the probabilistic interpretation, that the wave function gives probabilities, not physical densities, and the interpretation was eventually accepted by the physics community, though not by Schrödinger himself. Schrödinger himself was uncomfortable with the probabilistic interpretation of his equation. He devised the famous thought experiment of Schrödinger's cat, a cat in a box that is simultaneously alive and dead until someone opens the box and looks, not as a celebration of quantum mechanics but as a criticism. He intended the thought experiment to show how absurd the probabilistic interpretation was. Instead, it became the most famous illustration of quantum superposition, endlessly reproduced in popular science and endlessly misunderstood. The thought experiment highlights the measurement problem, the deepest unresolved question in quantum mechanics. If the wave function describes reality and the wave function allows superpositions, why don't we see macroscopic objects in superpositions? Why is the cat either alive or dead when we open the box, not both? The measurement problem has generated dozens of competing interpretations of quantum mechanics, none of which is universally accepted. The Copenhagen interpretation says the wave function collapses upon measurement. The many worlds interpretation says the wave function never collapses. Instead, the universe splits into parallel branches, one for each possible outcome. The decoherence program explains the apparent collapse as a result of the quantum system interacting with its environment, losing its quantum coherence. Each interpretation agrees with every experiment ever performed. The disagreement is about what the mathematics means, not about what it predicts. The equations work, the interpretation remains open, and the equations are now being exploited in a new way: quantum computing. A quantum computer uses the superposition principle, the ability of a quantum system to exist in multiple states simultaneously, to perform certain calculations exponentially faster than any classical computer. The promise of quantum computing rests entirely on Schrödinger's equation. The equation describes how superpositions evolve, and the evolution is what performs the computation. Quantum computers powerful enough to break current encryption schemes don't yet exist, but they're being actively developed by Google, IBM, Microsoft, and dozens of other organizations. If and when they arrive, the encryption that protects your data will need to be replaced, and the replacement algorithms are already being designed using mathematics that Schrödinger's equation describes. And Schrödinger's cat, conceived as a critique, has become the mascot of a mystery that physics has not yet solved. There is a companion to Schrödinger's equation that deserves mention: the Dirac equation, published by Paul Dirac in 1928. While Schrödinger's equation works for particles at low speeds, the Dirac equation extends quantum mechanics to particles moving at speeds close to the speed of light, incorporating Einstein's special relativity into the quantum framework. The Dirac equation predicted something nobody expected: antimatter. The equation has solutions corresponding to particles with negative energy, which Dirac initially couldn't interpret. He eventually proposed that these solutions correspond to particles identical to ordinary particles, but with opposite charge: positrons, the antimatter counterpart of electrons. The positron was discovered experimentally by Carl Anderson in 1932, confirming Dirac's prediction and establishing that antimatter is real. The discovery of antimatter from a mathematical equation, not from an experiment, not from an observation, but from the internal logic of the mathematics, is one of the most dramatic examples of the predictive power of equations. Dirac trusted the mathematics. The mathematics said antimatter exists. He looked for it, and it was there. The universe obeyed the equation. Antimatter, predicted by Dirac's mathematics in 1928 and confirmed by experiment in 1932, is now produced routinely in particle accelerators and used in medical imaging, PET scans, positron emission tomography. Work by detecting the gamma rays produced when positrons from a radioactive tracer annihilate with electrons in the patient's body. The medical technology that helps diagnose cancer exists because a theoretical physicist trusted an equation that predicted something nobody had ever seen. Dirac himself was famously taciturn. He spoke in short, precise sentences and avoided small talk with an intensity that bordered on the pathological. His colleagues at Cambridge told stories about his literalness. When someone said, "It's a nice day," Dirac reportedly went to the window, checked the weather, and replied, "Yes." The precision of his language mirrored the precision of his physics. Both were stripped of everything unnecessary. Schrödinger's equation is the last equation on our page that belongs to physics. To the description of the physical world, the remaining equations belong to different domains: information, finance, and the flow of fluids. But they all share something with the physics equations. They describe reality with mathematical precision, and the precision produces both power and surprise. In 1948, an American mathematician and electrical engineer named Claude Shannon published a paper titled A Mathematical Theory of Communication that created an entirely new field, information theory. Shannon's paper introduced the concept of the bit, the binary digit, the fundamental unit of information. A bit is the answer to a yes or no question. A coin flip produces one bit of information. A roll of a six-sided die produces roughly 2.6 bits. Shannon showed that any source of information can be measured in bits, and that the bit is the natural unit for quantifying uncertainty, communication capacity, and data compression. The bit is now so fundamental to technology that it's hard to remember it didn't exist before 1948. Before Shannon, there was no unit of information. Communication engineers talked about signals and noise, bandwidth and distortion, but they had no mathematical framework for quantifying the information carried by a signal. Shannon provided the framework, and the bit was its unit. Shannon's paper also introduced a quantity called information entropy, defined by an equation that looks almost identical to Boltzmann's entropy formula, but applies to messages rather than physical systems. Shannon's entropy measures the uncertainty of a message source. If a source can produce many different messages with equal probability, the entropy is high. Each message carries a lot of information, because you couldn't have predicted it in advance. If a source produces one message most of the time, the entropy is low. Each message carries little information, because you could have guessed it. This seems abstract until you realize its consequences. Shannon proved that the entropy of a source determines the minimum number of bits needed to encode its messages without losing information. This result, called the source coding theorem, is the theoretical foundation of all data compression. Zip files, MP3 encoding, JPEG compression, video streaming, and every other compression technology you use is an application of Shannon's theorem. The minimum file size is determined by the entropy of the data, and no compression algorithm can beat this limit. Shannon's work also explains why digital communication is superior to analog communication. In an analog system, noise degrades the signal at every stage. Each amplification, each transmission, each recording adds a little more noise, and the degradation is cumulative and irreversible. In a digital system, the signal is encoded as a sequence of bits, and each bit is either 0 or 1. Small amounts of noise don't change a 0 to a 1 or vice versa, so the signal can be regenerated perfectly at each stage. The superiority of digital over analog is a consequence of Shannon's framework. Digital communication operates closer to the theoretical limit than analog communication can. Shannon also proved a theorem about communication channels, noisy channels where errors can occur during transmission. The channel coding theorem says that for any channel with a given noise level, there exists a maximum rate at which information can be transmitted reliably. Below this rate, you can make the error probability as small as you like by adding redundancy, extra bits that encode the message in a way that allows the receiver to detect and correct errors. Natural languages use redundancy instinctively. English is roughly 50% redundant, meaning you can delete about half the letters in a typical English sentence and still reconstruct the meaning. Shannon's theorem quantifies the trade-off between redundancy and reliability. Below this rate, you can make the error probability as small as you like by using appropriate error-correcting codes. Above this rate, reliable transmission is impossible. This theorem is the theoretical foundation of all digital communication. Every cell phone call, every text message, every video stream, every file download operates within the limits Shannon's theorem defines. Engineers design communication systems to approach Shannon's limit as closely as possible, using error-correcting codes of increasing sophistication, turbo codes, low-density parity check codes, polar codes, each one getting closer to the theoretical maximum that Shannon proved exists. Modern 5G cellular networks operate within a few % of Shannon's limit. The engineering is extraordinarily sophisticated, but the target, the maximum achievable data rate for a given noise level, was calculated by Shannon in 1948, decades before the technology existed to approach it. Shannon didn't build 5G. He proved what 5G's maximum performance could be, and engineers spent 70 years building technology that approaches it. This theorem is the theoretical foundation of all digital communication, cell phones, internet, satellite links, deep space communication. The second time I felt something shift in how I understood mathematics was when I realized that Shannon's entropy and Boltzmann's entropy are not just analogous, they are one thing. Information is physical. The entropy of a message is the entropy of the physical system that stores it. Erasing information increases the entropy of the environment, releasing heat. This connection, explored by Rolf Landauer in the 1960s, means that computation has a fundamental thermodynamic cost. Every bit erased generates a minimum amount of heat, a result known as Landauer's principle, proved by Rolf Landauer at IBM in 1961. The minimum heat generated by erasing one bit at room temperature is roughly 3 times 10 to the negative 21 joules, an incredibly small amount but not zero. This means that computation is fundamentally irreversible and fundamentally thermodynamic. The same mathematics applies to biology. DNA is an information storage system, a sequence of 4 nucleotide bases that encodes the instructions for building an organism. The information content of the human genome is roughly 6.4 billion bits, or about 800 megabytes. Shannon's entropy can be applied to genetic sequences just as it can to text or digital signals, and the redundancy in the genetic code, multiple codons encoding for a single amino acid, can be understood in information theoretic terms. The information processing in your phone, in your laptop, in the server farms that run the internet, all generate heat that cannot be eliminated because erasing information increases entropy, and increasing entropy generates heat. Landauer's principle sets an ultimate physical limit on the energy efficiency of computation. Current computers are roughly 1 billion times less efficient than this limit, which means there is room for enormous improvement, but the limit exists, and it exists because of the connection between Shannon's information entropy and Boltzmann's thermodynamic entropy. The connection is not an analogy, it is an identity. The laws of thermodynamics and the laws of information are the same laws, seen from different angles. Shannon's paper is often cited as the most important master's thesis ever written, though the information theory paper was not his thesis. His actual master's thesis, written at MIT in 1937 when he was 21, showed that Boolean algebra could be used to analyze and design switching circuits. This result laid the theoretical foundation for digital circuit design and is considered one of the founding documents of the digital age. Shannon had 2 world-changing ideas before he was 35. During World War II, Shannon worked on cryptography at Bell Labs, where he developed a mathematical theory of secrecy systems that paralleled his later work on communication. He proved that a message encrypted with a truly random key of equal length, a one-time pad, is perfectly secure, unbreakable by any method. This result, which connects information theory to cryptography, established the theoretical limits of code breaking decades before the digital encryption systems that now protect the internet. Shannon, unlike many of the figures in tonight's story, lived a long and happy life. He spent his later years at MIT juggling, riding unicycles through the hallways, building mechanical devices, and occasionally publishing papers that revolutionized whatever field they touched. He died in 2001 at the age of 84, having created the mathematical framework that makes the entire digital world possible. His influence extends into artificial intelligence, where information theoretic concepts, entropy, mutual information, cross-entropy, are used to train and evaluate neural networks. The cross-entropy loss function, which measures the difference between a model's predictions and the actual outcomes, is derived directly from Shannon's entropy. Every time a language model is trained, every time an image classifier is optimized, Shannon's mathematics is running underneath. Shannon also anticipated the field of machine learning in a remarkable 1950 paper, in which he described a machine that could learn to play chess, not by being programmed with rules, but by playing games and improving from experience. The paper, written decades before practical machine learning existed, outlined the basic idea of learning from data that now drives the entire field. If you are drifting off, the equations continue without you. They've been running since before anyone wrote them down, governing the motion of planets, the flow of heat, the propagation of light, and the behavior of atoms. They don't need an audience. But if you're still listening, we have 2 more equations, one that nearly destroyed the economy, and one that nobody can solve. Shannon's influence extends beyond communication and into the deepest questions of physics. Jacob Bekenstein and Stephen Hawking showed in the 1970s that black holes have entropy, and the entropy is proportional to the area of the event horizon, not the volume. This result, which connects thermodynamics, general relativity, and information theory, suggests that the information content of any region of space is limited by the area of its boundary, not its volume. This idea, called the holographic principle, implies that the three-dimensional universe might be, in some deep sense, a projection from a two-dimensional surface. The mathematics that describes this possibility is Shannon's mathematics, applied to the fabric of space-time itself. The last equation on our page is the one that caused the most damage. Not because it was wrong, but because it was used as if it were more right than it actually was. In 1973, Fisher Black and Navier-Stokes published a formula for pricing financial options, contracts that give you the right to buy or sell an asset at a specified price on a future date. The Black-Scholes equation treats the price of the underlying asset as a random walk with normally distributed returns, and it derives an exact formula for the fair price of the option. Before Black-Scholes, options were priced by intuition, experience, and the balance of supply and demand on trading floors. Different traders could assign different prices to identical options, and there was no mathematical standard to determine who was right. Black-Scholes changed this by providing a formula that takes 5 inputs: the current stock price, the strike price, the time to expiration, the risk-free interest rate, and the volatility of the stock, and produces a single, definitive price. The formula works by constructing a hedging strategy, a combination of the option and the underlying stock that is risk-free, meaning its value doesn't depend on whether the stock goes up or down. The existence of this risk-free hedge determines the fair price of the option, because any other price would allow arbitrage, a guaranteed profit from a riskless transaction. The formula is not a prediction of what the stock will do. It is a calculation of what the option must cost, given the assumption that no arbitrage opportunities exist. The mathematical technique underlying the formula is stochastic calculus, extended to handle random variables. The stock price is modeled as a stochastic process, a mathematical object that evolves randomly over time, and the option price is derived by solving a partial differential equation that describes how the option's value changes as the stock price changes. The mathematics is beautiful, sophisticated, and exactly right, given the assumptions. The assumptions are where the danger lies. The formula was so useful that traders began carrying programmable calculators with the Black-Scholes formula built in, and the options market exploded in volume. The Chicago Board Options Exchange, which had opened in 1973, the year Black-Scholes was published, grew from trading a few hundred contracts per day to thousands, then tens of thousands. The equation didn't just describe the market, it created the market. The formula was elegant, practical, and immediately adopted by the financial industry. It transformed Wall Street. Before Black-Scholes, options were priced by intuition and negotiation. After Black-Scholes, they were priced by equation. The equation made it possible to trade options in enormous volumes with standardized pricing, creating the modern derivatives market. Scholes and Robert Merton, who independently derived similar results, received the Nobel Prize in Economics in 1997. Black had died in 1995 and couldn't share the prize. The problem was the assumption. The equation assumes that price changes follow a normal distribution, the bell curve. Under this assumption, extreme events, crashes, panics, sudden collapses, are improbable, that they can be safely ignored. A daily price swing of 10 standard deviations, which corresponds to roughly a 20% drop, should happen roughly once in the lifetime of the universe according to the bell curve. It has happened multiple times in the last 40 years. The most dramatic early warning came in 1998, when Long-Term Capital Management, a hedge fund founded by Scholes and Merton themselves, the creators of the model, collapsed after the Russian financial crisis triggered losses that the model said were virtually impossible. The fund lost $4.6 billion in 4 months and had to be bailed out by a consortium of banks to prevent a systemic financial crisis. The very people who created the equation couldn't protect themselves from its limitations. The stock market crash of 1987, the long-term capital management collapse of 1998, the financial crisis of 2008. Each time, events that the model declared virtually impossible actually occurred, and the financial institutions that had relied on the model's risk estimates suffered catastrophic losses. The 2008 crisis was the worst. Banks had used Black-Scholes and related models to price complex mortgage-backed securities, declaring them safe investments. When the housing market collapsed, the securities that the models had declared virtually risk-free turned out to be worthless. The resulting financial crisis destroyed trillions of dollars in wealth, cost millions of people their homes and jobs, and triggered the worst economic downturn since the Great Depression. Unemployment in the United States rose to 10%. Millions of families lost their homes to foreclosure. The stock market lost roughly 50% of its value. The effects rippled across the globe. Iceland's banking system collapsed entirely. Greece entered a debt crisis that would last a decade, and the European Union was shaken to its foundations. The total wealth destroyed by the crisis has been estimated at over $20 trillion. $20 trillion in losses, traceable in significant part to the use of a mathematical model whose assumptions didn't match reality. The model said extreme events were almost impossible. Reality said they happen every decade or so. The gap between the model and reality was measured in trillions of dollars, and millions of human lives disrupted, and triggered the worst economic downturn since the Great Depression. The equation wasn't wrong. The equation is mathematically correct, given its assumptions. The assumptions were wrong. Real financial markets have fat tails. Extreme events are far more common than the bell curve predicts. Using the normal distribution to model financial risk is like using a map of Kansas to navigate the Himalayas. The flat parts are accurate. The mountains aren't on the map, and the mountains are where the danger is. The mathematician Benoit Mandelbrot, famous for his work on fractals, spent years documenting the fat tails of financial returns. He showed that cotton prices, stock prices, and other financial quantities exhibit far more extreme movements than the normal distribution predicts. Mandelbrot proposed alternative distributions, stable distributions with infinite variance that better capture the wild swings of financial markets. His work was largely ignored by the financial industry, which preferred the mathematical tractability of the normal distribution to the inconvenient truth of fat tails. Nassim Nicholas Taleb, a former options trader turned writer, popularized Mandelbrot's critique in his book The Black Swan, published in 2007, the year before the financial crisis vindicated its thesis. Taleb argued that the most consequential events in history are precisely the ones that standard models declare improbable. Wars, financial crashes, technological disruptions, pandemics. The Black Swan thesis is, at its core, a critique of the Black-Scholes assumption. The world has fatter tails than the bell curve allows. The Black-Scholes story is a warning about the relationship between equations and reality. An equation is a model. A model captures some features of reality and ignores others. When the ignored features matter, when the mountains are present even though the map says they aren't, the model fails, and the consequences of the failure are proportional to the confidence that was placed in the model. The more you trust the equation, the more you bet on it. The more you bet on it, the more catastrophic the failure when the equation's assumptions turn out to be wrong. This is the deepest lesson of the Black-Scholes story, and it applies to every equation on tonight's list. An equation is a model of reality, not reality itself. F equals ma assumes that mass is constant, which breaks down at speeds approaching the speed of light. Maxwell's equations assume a classical electromagnetic field, which breaks down at the quantum level. Schrodinger's equation assumes non-relativistic particles, which breaks down at high energies. Every equation has a domain of validity, and outside that domain, the equation is wrong. The art of physics, and of finance, and of engineering, and of any field that uses equations, is knowing where the boundaries are. Every equation is a map. Every map omits details, and the omitted details are sometimes the ones that matter most. The Black-Scholes story is the darkest equation story on tonight's page, but it's also the most instructive. It shows that equations are tools, not truths. They capture aspects of reality with extraordinary precision, but they always leave something out. The something they leave out can be harmless or catastrophic, depending on how much weight you place on the equation's predictions. Trust the equation within its domain and it serves you brilliantly. Trust it beyond its domain and it destroys you. The more you trust the map, the harder you fall when the terrain doesn't match. There is one more equation that belongs on this page, though it differs from the others in a fundamental way. It is the Navier-Stokes equation, and it describes the flow of fluids, water, air, blood, magma, the atmosphere, the oceans, the gas clouds between stars. The equation has been known since the 1800s. It works. Numerical solutions match experimental observations with extraordinary precision. Airplanes are designed using it. Weather is predicted using it. Every weather forecast you've ever seen was generated by solving the Navier-Stokes equations numerically on a supercomputer, starting from current atmospheric conditions and running the equations forward in time. The forecast is accurate for a few days and then degrades rapidly, not because the equations are wrong, but because turbulence amplifies small uncertainties in the initial conditions into large uncertainties in the predictions. This is the butterfly effect. A butterfly flapping its wings in Brazil can, in principle, trigger a tornado in Texas. Not because the butterfly causes the tornado, but because the tiny air disturbance changes the initial conditions in a way that, amplified by turbulence, produces a dramatically different outcome weeks later. Weather is predicted using it. Ocean currents are modeled using it. The Gulf Stream, the Kuroshio current, the deep thermohaline circulation that distributes heat around the planet, all governed by the Navier-Stokes equations applied to seawater. Climate models, which simulate the behavior of the atmosphere and oceans over decades and centuries, solve the Navier-Stokes equations on grids covering the entire planet. With millions of grid cells, each one a tiny region of atmosphere or ocean whose temperature, pressure, and velocity are tracked over time. The computational cost is staggering. Climate simulations run on the largest supercomputers in the world for months, and the accuracy is limited by the same turbulence problem that makes weather prediction difficult beyond a few days. Ocean currents are modeled using it, but nobody knows whether the equation always has smooth solutions. The equation is nonlinear. The fluid's velocity appears multiplied by itself, and nonlinear equations are notoriously difficult to analyze. Small changes in initial conditions can produce wildly different outcomes, which is why weather prediction is so hard beyond a few days. The atmosphere is a fluid. Its behavior is governed by the Navier-Stokes equations, and the equations are chaotic, sensitive to initial conditions in ways that amplify small uncertainties into large errors. The turbulence problem is the heart of the difficulty. Laminar flow, smooth, orderly fluid motion, is well understood. Turbulent flow, the chaotic, swirling, unpredictable motion you see in a rushing river or a smoke plume, is not. Turbulence is described by the Navier-Stokes equations, but solving those equations for turbulent flow is so difficult that Richard Feynman called turbulence the most important unsolved problem of classical physics. Nobody knows whether the equation always has smooth solutions. Given a smooth initial condition, a smooth description of the fluid at time zero, does the Navier-Stokes equation always produce a smooth description of the fluid at every future time? Or can the solution develop a singularity, a point where the velocity becomes infinite, where the mathematics breaks down, where the equation stops making sense? Nobody knows. The question is one of the 7 Millennium Prize problems, with $1 million reward for a solution. The equation that describes every fluid flow you have ever seen, from a dripping faucet to a hurricane to the blood in your veins, rests on a mathematical foundation that hasn't been proved to be sound. It probably is sound, but probably is not a proof, and in mathematics the distance between probably and proved is the distance between conjecture and certainty. The Clay Mathematics Institute included the Navier-Stokes existence and smoothness problem in its list of 7 Millennium Prize problems in the year 2000, alongside the Riemann hypothesis, the P versus NP problem, and 4 others. Each problem carries a prize of $1 million. Only one has been solved, the Poincaré conjecture, by Grigori Perelman, who declined both the prize and the Fields Medal. The Navier-Stokes problem is the only Millennium Prize problem that concerns a physical equation, an equation that engineers use every day to design aircraft, predict weather, and model ocean currents. The equation works. Engineers trust it, but mathematicians cannot prove that it always produces well-behaved solutions, and the inability to prove this is both humbling and fascinating. The most practical equation in all of physics rests on a mathematical foundation that is still, after nearly 2 centuries, incomplete. We started with a page. 17 equations on a single page, each one a story, each one a person who saw something nobody had seen before. Pythagoras and the shape of triangles. Euler, and the topology of solids, Newton and the grammar of motion, Euler again and the unity of constants, Maxwell and the nature of light, Boltzmann and the arrow of time, Einstein and the equivalence of mass and energy, Schrödinger and the probability of everything, Shannon and the physics of information, Black-Scholes and the price of risk, Navier-Stokes and the flow of fluids. Each equation fits on a line. Most can be written with fewer than 20 symbols, and each one encodes, in those few symbols, a truth about the universe that took centuries of human effort to extract. The ratio of symbol count to insight density is absurd. A dozen characters describing a truth that governs the behavior of every object in the universe, or every electromagnetic wave, or every quantum particle. The compression is part of what makes equations powerful. A truth that can be stated in a line can be applied in a line, can be taught in a line, can be transmitted from one generation to the next in a line. An equation is not a description. It is a relationship, a precise, quantitative, testable relationship between quantities. F equals ma doesn't describe motion. It relates force to acceleration through mass. E equals mech squared doesn't describe energy. It relates energy to mass through the speed of light squared. The distinction between description and relationship is crucial. Descriptions can be vague, approximate, qualitative. Relationships are exact, testable, and falsifiable. A description can be vague and still be right. The sky is blue is true, but imprecise. A relationship can be wrong by the smallest amount and be definitively falsified. If F equals ma predicts a trajectory that misses by a millimeter, the equation is either wrong or incomplete. This falsifiability is what gives equations their power. They make predictions so precise that reality can check them, and reality always has the final word. And exact relationships make predictions, and predictions can be tested, and tested predictions are the foundation of science. The equations are the most efficient storage medium for physical truth ever devised, and the efficiency is what makes progress possible. Each generation doesn't have to rediscover Newton's laws. They learn them in a line and build from there. Each equation fits on a line. Each one took centuries to find. And each one, once found, rearranged the world, not by force, not by decree, but by revealing a truth that had been there all along, waiting to be noticed, waiting to be written down, waiting to be understood. The equations don't need you to understand them. They were true before anyone wrote them down, and they'll be true after every blackboard has been erased. But the fact that humans found them, that people sitting at desks and staring at problems for years and decades and lifetimes managed to extract these truths from the noise of the universe, that is, in its own quiet way, one of the most remarkable things our species has ever done. Each equation on this page made the next one possible. Without the Pythagorean theorem, there is no concept of distance, and without distance, Newton can't write F equals ma. Without Newton, Maxwell can't describe electromagnetic fields. Without Maxwell, Einstein can't derive special relativity. Without special relativity, there is no E equals mc squared. Without quantum mechanics, there are no semiconductors. And without semiconductors, Shannon's information theory has nothing to run on. The dependencies run deeper than chronology. The mathematical techniques needed to work with one equation are often derived from working with earlier ones. Euler's work on differential equations, developed partly to solve problems in Newton's mechanics, provided the tools that Maxwell used to formulate electromagnetism. Fourier's analysis of heat flow, which was motivated by Boltzmann's thermodynamics, provided the tools that Shannon used to analyze communication channels. The equations are linked not just by the physics they describe, but by the mathematical techniques they share. The chain is not a metaphor. It is the actual historical and logical structure of physics and mathematics, each link forged by a specific person solving a specific problem, each link supporting every link that follows. The page is still open. There are equations we haven't found yet. There are equations we haven't imagined yet. The Navier-Stokes question is still unanswered. The equation for quantum gravity hasn't been written down. The equation that unifies quantum mechanics with general relativity, the theory of quantum gravity, hasn't been written down. String theory proposes candidates. Loop, quantum gravity proposes others. Neither has been confirmed by experiment. The equation that explains dark matter, the invisible substance that makes up roughly 27% of the universe's mass-energy content, is unknown. The equation that explains dark energy, the mysterious force that is accelerating the expansion of the universe, is unknown. The page of equations is incomplete, and the missing equations may be more important than the ones we have. But the equations we have already explain an astonishing fraction of the observable universe, from the structure of atoms to the orbits of planets, from the flow of rivers to the transmission of data, from the arrow of time to the price of risk. The equations on this page cover it all. The remaining mysteries are at the extremes: the very large, the very small, the very fast, the very dense. The everyday world, the world you'll live in, the world you'll wake up in tomorrow, is described by these equations with a precision that borders on the miraculous. But the equations we have, the equations on this page, are enough to build the world you live in, to explain the universe you inhabit, and to remind you as you drift towards sleep that the universe is comprehensible, not because humans are clever, but because the universe has structure, and that structure can be captured in equations, and the equations fit on a page. The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Why should the universe be describable by equations at all? Why should identical equations that describe the motion of a pendulum also describe the oscillation of a spring, the vibration of a guitar string, and the behavior of an electromagnetic wave? Why should the universe be so generous with its patterns, so willing to reveal its structure to anyone patient enough to look? Nobody knows. The unreasonable effectiveness of mathematics is itself one of the great unsolved mysteries, not a mathematical mystery but a philosophical one, a question about the relationship between the abstract world of equations and the physical world of matter, energy, space, and time. Not fully comprehensible, not yet, but comprehensible enough that a single page of equations can hold most of what we know, and that the page is still being written. Someone, somewhere, tonight, is working on the next equation. They might be a graduate student in a cramped office. They might be a professor at a blackboard. They might be a patent clerk working in their spare time, scribbling equations that nobody else has seen. The next equation might explain dark matter. It might unify quantum mechanics with gravity. It might describe the initial conditions of the Big Bang. Or it might describe something we haven't imagined yet, a phenomenon, a relationship, a truth that is currently invisible, waiting for the right equation to make it visible. The page is still being written. Someone, somewhere tonight, is staring at a blank sheet of paper, or a whiteboard, or a computer screen, trying to find the next equation. The equation that explains dark matter. The equation that unifies gravity with quantum mechanics. The equation that describes the initial conditions of the universe. Or an equation nobody has imagined yet, solving a problem we haven't learned to ask. The page has room. The page always has room. The equations are small and the universe is vast, and the distance between what we know and what we don't know is the distance that drives every mathematician and every physicist forward. The distance that has been driving them forward for 25 centuries, from the Pythagorean theorem to the equations that haven't been written yet. The page is still open. The pen is still moving, and the universe is still waiting to be described. And that is more than enough to carry into sleep.